In my hand, I have some legumes. The production of legumes, together with the production of the world crop, has to increase by 70% in order to support a population that is going to grow from 8 billion people to 10 billion people, so by 25%. And this is because we're not only producing food to support ourselves, but also to support the animals we're feeding on and to support energy production. 700 million people are currently undernourished and they don't have access to food. They live in food insecurity. And agriculture alone is responsible for 10% of greenhouse gas emission. You can clearly see that we need to reinvent the agricultural system so that they become more precise, more resilient to climate, and more importantly, they can distribute food more equally to everybody. And at the center of these reinventions, there are fertilizers. Synthetic fertilizers have supported human well-being for the past decades. However, their production is very intensive. 2% of the world energy goes to produce nitrogen-based fertilizers. Phosphate-based fertilizers are a limited resource. The distribution of fertilizers around the world is also non-homogeneous. Looking at the distribution, it's clear that there are regions in the world where fertilizers are not deployed. And these are the regions where food insecurity prevails, and more importantly, where the majority of the population growth is going to occur. And so we need to be able to change the system in order to support our health. There are several technologies that are understudied, and one of them are biofertilizers, which are microbes that are plant growth promoting. These microbes live in the soil. They can fix nitrogen, solubilize phosphate, mobilize micronutrients that can be loaded in the next generation of crops. And at the same time, they mitigate climate stressors that threaten agriculture. One bottleneck remains, though. How can we successfully apply these biofertilizers? The scientific community is coming together to understand how we can use them so that we can support agriculture, but the bottleneck remains. And what if we found solution in waste? Particularly, what if the solution is in biomass, in the byproduct of agriculture, food, and textile industry? We can extract biopolymers from the biomass. These are natural polymers that can be upcycled to become technical materials and that can be used to encapsulate and release the biofertilizers. Among all the biomass, one of the most interesting comes from crustacean. This is a relatively clean biomass that is made by two phases, a mineral phase, calcium carbonate, and another that is made by biopolymers. Crustaceans are limited in space, so we can think about extracting them and then deploy them as technical materials. Of course, the polymers they will extract from it. And particularly, the starting point is chitin, which is a complex biopolymer, which can be deacetylated to make chitosan, which is a polysaccharide that is water-soluble. Chitosan can also be designed to be cross-linked with sugars, and the combination of chitosan with sugars is able to host and protect biofertilizers also in the dry state, so that formulations can be made out of chitosan, sugars, and biofertilizers, which can be sprayed on the surface of seeds to make seed coats. The seed coats is a very benign way to deliver biofertilizers because they don't require refrigeration. The same supply chain of seeds can be used, and a single dose of biofertilizer can be useful to deliver the required amount of nutrients into the soil. There are several parts of the world where biofertilizers are deployed. One of the frontiers is in Morocco, because there, what scientists are looking at is not only the effects on reducing the amount of synthetic fertilizers that are used, but they're also looking at how to unlock new land, how marginal land that cannot currently support agriculture, how it can be converted to a land that instead can give us more food. There are several farms in climates that are arid, super arid, and semi-arid. And among these farms, the interesting result is that when the seeds are coated with the seed coat, plants grow faster and better and are more resilient to harsh climate conditions. And particularly, if the look goes towards the crop production, the crops that are made are biofortified. So not only more crops can be grown, but the crops also possess more micronutrients inside. This is because the microbes that are released in the soil increase the soil biodiversity, and at the same time, this biodiversity of microbes is able to solubilize micronutrients that are then absorbed in the roots and loaded into the next generation of crops. Among the micronutrients that are loaded, one of the most important ones is zinc, because there is a hidden hunger for zinc in the world, in the United States, but more specifically in parts of the world where really food security has a high impact on human well-being. And so, as we're going to re-engineer agriculture, what I hope is that the next time you take beans to make your bean soups, these beans are more nutritious, they are grown in parts of the world where agriculture is not possible nowadays, and more importantly, they are grown to increase biodiversity and with less energy. Thank you very much for your attention.